Hello everyone, and welcome to this video titled Derivatives of Inverse Functions. So in this video, I'm going to be taking you through a preview version of a Knewton Alta homework assignment that is also titled Derivatives of Inverse Functions. So please understand that this is a preview version I'm working on. So the questions that I'll be working on in this video may not be exactly the same questions that you'll be working on if you're working on it as a student. But the objectives are the same, and the methods for working on the problems should be pretty similar. So hopefully watching this here will help you when you do it on your own. All right, so here we are at Knewton Alta, and a preview of this derivatives of inverse functions assignment, which for the particular course I'm teaching here is section 3.7. In the upper right-hand corner, you should be seeing a mastery bar. This just tells you how far along you've gotten in the assignment. Next to that, an activity log, which shows you all the objectives of the assignment. So this particular assignment has just the one objective. So be doing the same objective for every question here. So we have our current objective back on the main page, a question related to that objective, and then at the bottom of every question, you should see a feedback button. So if you notice anything wrong with the question or with the answer explanations after the question, please submit feedback. You can do this directly to Knewton support, and hopefully they'll see it soon enough and get back to you quickly to help you address whatever issue you may have. This instructor cheat button will not be there, of course, right? This is for instructors only, just to fill in answers when making presentations and whatnot. So I will not be using this in this video since you won't have it either. But you will see the more instruction button. So if you're working on a question and a particular objective that you don't really remember the material too well, click on more instruction and you'll be given some reading to do or videos to watch or both. Um, that will hopefully help you, refresh your memory as to what the material is about and help you get through the assignment that way. Okay, so as mentioned, there's only one objective here. Find the derivative of an inverse trigonometric function. So not just inverse functions, but specifically inverse trigonometric functions. So before I get into the question, I want to do a little discussion on the derivatives of inverses and then specifically these inverse trig functions. So inverse functions. Now I'm making the assumption here that you've seen functions that are inverses in a trigonometry class or algebra or pre-calculus class of some sort. So a lot will be assumed of you here, but you may recall that when you compose two inverses, so say F inverse, the little minus one there, remember that meant inverse of F, that was just the reverse mapping. Just a recap here, like if an ordered pair, let's say A comma B was on the graph of F, then again, reverse the mapping, reverse the order of the x and y values, switch the x and y values, then B comma A, right, was on the graph of its inverse. And again, F with the little -1 there. So you may recall that when you compose two inverses, so again, say F inverse, little circle here, composed with F of X, they just, again, reverse one another. They undo each other. And you're left with just X. And this, of course, is as long as X is in the domain of F, right? Make that note. Right, because you have to plug X into F first, and then take F of X and put it into F inverse, and that'll take you right back. All right, so like if my input were A, then the output would be B, and then I would put B into the F inverse function. It would take me right back to A, right? You're taken right back to where you start from. Now, if we apply the chain rule to our composition here, so I'm going to write it this way, where you have F inverse, composed with F of X, like this, F inverse of F of X. Well, since this is equal to X, say I were to take the derivative of this, like let's say this is y equals, say the output says y equals x, y equals this F inverse composed with F. Then applying the chain rule, y prime, or the derivative of such a thing, would be, the derivative of F inverse. So this is F inverse prime, right? The outer function. Remember, with the inner function still inside it, right? This F is inside F inverse up here. So F will also be inside F inverse prime down here. And then times then the derivative of the expression inside, right? F prime of X. So that's applying the chain rule to this, right? Composition of F inverse and F. But this is supposed to be just equivalent to X, right? And if Y is equal to just plain old X, remember the derivative of just plain old X was 1. Then solving for F prime here, so getting this F prime alone, so F prime of X is equivalent to 1 over, as long as this is not 0, you can divide by it. So we're making that assumption. The derivative of F inverse, so F inverse prime, with the original F put inside. Okay, so this is something you'll see in some text, this rule here. So this is a rule showing you the relationship between derivatives of functions and the derivatives of their inverses. See, they're reciprocals. So the derivative of one function is 1 over the reciprocal of the derivative of its inverse with the original function inside. Right, so again, as long as these are inverses, right, so I have f here, and then f inverse down here, the function being primed or derivative, taking the derivative of over here, is the inverse of the function being primed or taking the derivative of down here. And then the expression inside that denominator's function derivative, right? The expression inside this f inverse prime down here is just the original of, whatever this one was out here. Right? So not, out here is f prime, inside here is just plain old f. So again, I'm going to use this now when it comes to the inverse trig functions. And just like with the derivatives of the trig functions, regular trigonometric functions in a previous video, I'll pull up Desmos and kind of refresh your memory as to what the graphs of these things look like. I'll keep bringing up this rule here. This is, derivatives, how derivatives of inverses are related. I'll keep bringing this up when it comes to the derivatives of the inverse trig functions. Okay, so now we're doing the derivatives of the inverse trigonometric functions. This is the only objective in this section. So first, go over inverse sine. So that's, say f of x equals this sine with the little -1 above it, right? This is the inverse sine of x. Or you might have seen this again from a trig class, arc sine of x. Right? These mean the same thing. Now I'm going to point out that if f here is the inverse of sine, then f's inverse function, the inverse of this, would be just regular sine. Right, again, these are inverses of one another. So just plain old sine of x over here. Now, to remind you of what the graph looks like, the graph of arc sine or inverse sine of x, and make sure you're in radians and all that, right? So the input's going to be a value and the output will be in radian measure. So I'm just going to go, y equals arc sine. I like the arc. So that was this here, just this little piece of graph. We had 0, 0, so it was like part of the sine wave, but going up and down instead of left and right. And you had, 1 pi over 2 was this highest point, and then -1, negative pi over 2, this lowest point, and it curved up like this. And hopefully you can see from the picture here that when I find the derivative, right, when I go find the derivative, the slopes of the tangent lines to this curve, it's going to be some positive value all the time, right? This is always going up as I go from left to right. Say a domain was -1 to 1, range, negative pi over 2 to pi over 2, and again had this look to it. So I'll put that rule up, that function, that relationship between the derivatives of inverses rule I had on the previous page, right? So if f is this inverse sine function, right, again, then f prime should be the reciprocal of, right, 1 over, and then the derivative of the inverse, right, so f inverse prime, which is the derivative of plain old sine, with the original function I'm looking at, this inverse sine, this arc sine function, put inside. So I'm going to keep referring to this. So in order to calculate, this expression on the right side here to get my derivative of the inverse sine function, I need f inverse, prime. Well, again, f inverse, the inverse of the inverse sine is plain old sine. Remember, the derivative of that was cosine of x. So down in the denominator here, I have 1 over the cosine of, but not cosine of just x, right? It's cosine with whatever the original f, the original function whose derivative we're taking here is. So with the inverse sine put inside there, right, replace x in cosine x with the inverse sine, arc sine of x. And here we go. All right. So here is a perfectly valid expression for the derivative of the inverse sine function. It's, 1 over the cosine of the inverse sine of x. And again, that's totally fine. This works. However, you may recall from trigonometry class, or again pre-calculus, that you can take the cosine of an inverse function, or again where you have a regular trig function on the outside and then some inverse trig function on the inside. You can rewrite this algebraically. Right, so when they say algebraically, that means using just addition, subtraction, multiplication, division, and roots with your numbers and letters, right? So no trigs or inverse trigs. Okay, so recall that, when we're talking about the inverse sine of some number, right, this arc sine of x inside here, this is an angle measure. Right? When you plug a number into the inverse trig functions, your output is some angle measure. And we saw in the graph that it's an angle measure from negative pi over 2 to pi over 2. So instead of writing all these words out, angle measure from negative pi over 2 to pi over 2, right, this angle measure we're going to call theta. And I'll go to the xy plane here, and we'll draw an angle between negative pi over 2 and pi over 2, in standard position. So starting at the origin here with the positive x-axis. Now, negative pi over 2 to pi over 2, remember negative angles are clockwise, positive angles are counterclockwise, so that's the right half. All right, here's negative pi over 2 to pi over 2, that's just the right half of the plane. So I'll start initially with being in quadrant 1. So let's say this angle, right, this inverse sine of x, this theta, is here in quadrant 1. I'll make a little right triangle to go along with that. Set this up so that it's, sine is x, right? Because if the inverse sine of x is theta, that means, the sine of theta must be x, or x over 1. Remember, sine was opposite over hypotenuse. So opposite length here on the right triangle x, hypotenuse 1. And then through use of the Pythagorean theorem, you can show that this horizontal length would have a length of, positive square root of 1 minus x squared. Now, looking at this picture, see how we're asked to determine here 1 divided by the cosine of this inverse sine of x, which I called theta. And if you go to the picture, the cosine of theta in this right triangle, remember that's adjacent over hypotenuse. So that's the square root of 1 minus x squared, over 1. So that's going in the denominator here, right, replacing this cosine of theta. So here we go. This is, the algebraic version of the derivative. And we're just adding, subtracting, multiplying, dividing, and roots involved with our letters and numbers. So there we go. That's it there. So f prime, and for inverse sine of x, or arc sine of x, the derivative function, the derivative at any x, is positive 1 divided by, the positive square root of 1 minus x squared. Okay, so I'll put this in a bubble. This is it. I would put this on a list somewhere, right? Add this to your list of derivatives you should know. And the same would go if I had an angle, that was also in the quadrant 4, right? If theta were negative, x would be, down here, x would be, this value down here, and then 1 for the hypotenuse, and it's still the same length, and it's still a positive quantity. So my cosine would still be this positive quantity, root of 1 minus x squared all over 1. So it wouldn't change, no matter what piece of the negative pi over 2 to pi over 2 we were part of. So same derivative each time. Great. All right, so derivative one more time. Derivative of inverse sine of x, inverse sine of something, is 1 over the square root of 1 minus, that thing squared. All right, so I'm going to do something similar for inverse cosine now. So again, we'll start with, just calling it plain old f. So now f of x is, the inverse cosine. So again, the cosine with the little -1 there, or the arc cosine of x. And back to Desmos here, I'm just going to change arc sine here to arc cosine, and we'll look at that picture once more. So that's this piece of curve, and that's it, right? So the top point, the highest point here is at -1 pi. And then it's like having a piece of the cosine wave, but opening up, going up and down instead of left and right. And the bottom point here is at 1, 0. And, y-intercept at 0 pi over 2. Say a domain, -1 to 1. The range, 0 to pi. So this time I'm going to be talking about angles from 0 to pi. So that'll be in the top half of the plane, the xy plane, when I draw an angle in standard position later. All right, so same deal as with the inverse sine, right? If my original function's called, inverse cosine, the inverse of that would just be plain old cosine, right? So f inverse, if that was called f, would just be regular, cosine of x. and then applying that same rule once more. Right, so I'll write it again. So the derivative of one function, right, so the one I want, the derivative of this inverse cosine function, what I called f. So f prime should be equivalent to the reciprocal of, right, 1 over the derivative of its inverse, right, f inverse prime, with the original f put inside that. So I'm probably not going to write this out every time, but at least a few times here. So to do this, to calculate this expression on the right side, I need the derivative of the inverse. Now again, the inverse of my function is plain old cosine. And the derivative, so f inverse prime here, the derivative of plain old cosine of x was the opposite of the sine of x. And then once again, I'll be putting the original function, right, my inverse cosine or arc cosine here, I'm going to be putting that inside this derivative. So the derivative of the inverse cosine function is going to be 1 over the derivative of regular cosine, so negative sine, with the inverse cosine put inside. So arc cosine of x or inverse cosine of x. And I'm going to put this negative up top, but still, so we have this is perfectly valid. Now this does represent the derivative, the slope of the tangent line, to that curve we were looking at for the inverse cosine function. Just once again, you see this regular trig with an inverse trig put inside, some angle measure. Remember the inverse trigs represent an angle measure. So I should be able to express this algebraically. All right, so once again, this expression inside the inverse cosine of x, this arc cosine of x, this is an angle measure, right, called theta. This is, though, an angle measure from 0 to pi. So if I were to draw some angle measures here on the xy plane in standard positions starting from the origin, so again, 0 to pi means, top half of the plane. Right, 0 radians, you're on the positive x-axis, and then pi radians, you're over here on the negative x-axis, so top half. So I'll break it up into two parts, right? How about what if the angle ended in quadrant 1, right? So between 0 and pi over 2, so say this was theta. So again, we want to set it up so that the cosine of this angle is x, whatever value I plug in for x here. So that's adjacent length x, hypotenuse 1, and then the vertical leg would again be, the positive square, because it's above the x-axis here. This would be a positive measure, have a positive y value, positive square root of 1 minus x squared. And something similar would happen even if I had my angle over here in quadrant 2. Say this was theta, and I'm ending over here. So again, there's some reference angle here, and remember the reference angles and have the same values of the trig functions, given a plus or minus. So this angle here, this reference angle, should also have a cosine of x, right? So adjacent length x, which over here that would be a negative length, right, as left of the origin. And then hypotenuse 1, but still the opposite side from the reference angle here would have a positive length still. That would still be positive square root of 1 minus x squared. So no matter how you look at it, no matter what quadrant we're in here from 0 to pi, this this opposite length to the angle or reference angle as a positive measure. And taking this, we're asked to, I'll put the negative up top here. So this is -1 divided by the sine of this arc cosine of x, which I'm calling theta. And from the pictures I've been drawing here, right, the sine of theta, and looking at the theta here, or the reference angle to theta over here, is opposite over hypotenuse, which in both cases is the positive, square root of 1 minus x squared. So I end up with, and I'll bubble this in, f prime is, -1 over, and then the sine of theta being the square root of 1 minus x squared. So there's your derivative of the inverse cosine of something, or arc cosine of something. It's -1 over the square root of 1 minus x squared. And you may notice that that is simply the opposite of the derivative of inverse sine, right? We saw on the previous page the derivative of inverse sine was +1 over the square root of 1 minus x squared. Inverse cosine, the derivative, is just the opposite of that, -1 over the square root of 1 minus x squared. And you're going to see that for all the inverse co-functions, right? So inverse sine, inverse cosine have opposite derivatives. Inverse tangent and inverse cotangent we'll see have opposite derivatives. And inverse secant and inverse cosecant will also have opposite derivatives. Okay, so that's inverse sine and cosine. We got 6 of these. So now let's go to inverse tangent and cotangent. So inverse tangent next. So now again the plain old f, the function I care about is inverse tangent, so tangent with a little -1 above it of x, or that arc tangent of x. And just another refresher as to what this looks like. So back to Desmos here, inverse tangent. So it was like this long, elongated S curve here. So the domain is all real numbers, you'll notice. You can plug in anything for x and get some output. And then the asymptotes, though, the highest value approaches, here's y equals pi over 2. See how as I move to the far right, the point on the red curve is getting closer and closer to this pi over 2 value. And then here's y equals, negative pi over 2. That's the asymptote to the left. As I go to the far left, the values are approaching negative pi over 2. So the domain is all real numbers. The range is from negative pi over 2 to pi over 2, but not including negative pi over 2 and pi over 2. So when I go to draw, angle measures later, it's going to be on the right half of the plane again, right, from negative pi over 2 to pi over 2 radians. So once again, to find the derivative of this, I need to use the derivative of its inverse. And these are inverses. So the inverse of the inverse tangent would be regular tangent. And remember the derivative of regular tangent of x was secant squared of x. So using that rule I've been putting up, I'm not going to write it this time. So the derivative of our inverse tangent function here, the derivative of this is going to be 1 over the derivative of regular tangent, so 1 over secant squared, but with not just x inside, but our original function, this inverse tangent of x, put inside. So the derivative of inverse tangent is 1 divided by 1 over the derivative of regular tangent, secant squared, with the inverse tangent put inside. And once again, this is totally valid. This is perfectly fine as the derivative of the inverse tangent function. But like all the others, going to be asked to, and you'll see this in most of your tables and derivative tables and whatnot, we're going to write this algebraically. So like all the other ones, right? The inverse tangent, this arctangent of x inside here. I'm going to call this theta again, right? This is an angle measure from pi over 2, negative pi over 2 to pi over 2, right? You saw in the graph. So the quadrants one, it could be a quadrant 1 angle or a quadrant 4 angle when I go to draw it. So we'll look at both. We'll look at both, right? So here's, between 0 and pi over 2, let's say theta was up here. So again, I set this up so that the tangent of this angle is x, right? If the inverse tangent of x was theta, then the tangent of theta must be x. So my right triangle here, right, tangent, remember, is opposite length. So this opposite length is x over adjacent. So this is a adjacent length of 1 unit here. And then Pythagorean theorem, you can show that this hypotenuse length is the square root of 1 plus x squared, or x squared plus 1. And it would have to be the positive square root, right? Because it's a length of a hypotenuse, so a length, hypotenuse length, distance from the origin, typically represented by a positive quantity. And it would go in a similar fashion even if I had my theta down here in quadrant 4, right? If I set up my triangle down here and set it up so that opposite length is x, adjacent length is 1, so the hypotenuse would still be 1 plus, x squared and then the square root of that, but, it's still the length of the hypotenuse. So even though this side has a negative, would say, you have right 1, so that's positive 1, and then down, x, so this would be a negative length. The length of the hypotenuse would still be considered a positive quantity. You'd still have the positive square root of 1 plus x squared. So in either one of these, the secant, because again, what we're trying to find here for our derivative of the inverse tangent function is 1 divided by, secant squared of this thing we're calling theta. And in each of these triangles, secant theta, and that's hypotenuse over adjacent, so that's, this square root of 1 plus x squared over 1. And then we're squaring this, right? So that gets rid of the square root. So secant theta squared is just 1 plus x squared, or x squared plus 1. So here we go. This is our derivative of the inverse tangent function. So the derivative of the inverse tangent of x of something is 1 divided by 1 plus that thing squared, 1 plus x squared. Wonderful. And then just like I mentioned earlier with inverse sine and inverse cosine, so we're going to see in a minute the derivative of inverse cotangent is just going to be the opposite of this, negative 1 over 1 plus x squared. But let's go through it. So fourth of these, right, inverse cotangent. So again, the function I care about, the original one, is this one I'm going to call f, the inverse cotangent, right? So cotangent with the little -1 of x, or arc cotangent of x. And again, just to remind you what that looks like, here's arc cotangent of x, right? So this swooping down curve. So domain's all real numbers, right? You can plug in anything. The range, however, though, is not from -pi/2 to pi/2, but from 0 to pi. So there's y equals pi in green. So that's the left asymptote, right? As I go to the far left, the output's approaching pi, but never actually becoming pi. And then the bottom asymptote, the right asymptote would be, the x-axis, y equals 0. As you go to the right forever, the output's approaching 0. So domain, all real numbers. Range is from 0 to pi, without including 0 or pi. So when I go to draw angles in the xy plane in standard position, I'm looking at quadrants 1 and 2, right, the top half of the plane. So again, if that's f, its inverse would be plain old cotangent. And the derivative of the regular cotangent, so f inverse prime here, was, the opposite of cosecant squared. And then I'm putting this, inside that. I'm putting the original function inside the derivative of the regular cotangent, right? And taking the reciprocal of that, right? So f prime, right, applying that rule I've been applying this whole video so far. So the derivative of the inverse cotangent is 1 over the derivative of regular cotangent, so negative cosecant squared, but with the inverse cotangent put inside. So again, arc cotangent, or inverse cotangent of x there put inside. So I'm going to put this negative up top, make this -1 in the numerator. But now we're trying to find, rewrite this expression here, which is totally fine. All right, this is this is the derivative of the inverse cotangent at any x. It's just, again, they're going to typically rewrite this algebraically. So the arc cotangent of x, I'm going to call that's an angle measure. Once again, call it theta. But this time, it's an angle from 0 to pi. So either a quadrant 1 or quadrant 2 angle, which I'll show both. So if it were a quadrant 1 angle, so let's say this is theta here. Again, I'm setting up my picture, right triangle, so that the cotangent of this angle is x. Now, cotangent was adjacent over opposite, so the adjacent length is x and the opposite length is 1. But still, the hypotenuse has a length of, still positive for all the hypotenusae are positive length in any of these pictures. And through the use of the Pythagorean theorem, that would be the square root of 1 plus x squared, or x squared plus 1. Yeah. And then even if it were a quadrant 2 angle, let's just say again theta was over here, and this was my triangle, and you got a reference angle that would have the same values of the trig functions, right? So same kind of setup. So set it up so that the cotangent of this reference angle was, x as well. So adjacent x, opposite 1. And then the hypotenuse is still the same value, right? Same looking thing, same expression, the positive square root of 1 plus x squared. Even though, this leg, the horizontal one, would have a, a negative value associated with it because it's, on the negative side of the x-axis. Hypotenuse still positive. Right? Hypotenuse always positive in these pictures. And what we want to find is the cosecant of theta. Right? This is a -1 over the cosecant of theta, squared. So in either of these pictures, whether you're a quadrant 1 angle or a quadrant 2 angle, the cosecant of theta, remember that's the reciprocal of sine, which would be hypotenuse over opposite. So for this angle here, or the reference angle to theta here, hypotenuse over opposite would be the square root of 1 plus x squared over 1. And then this is getting squared, right? So that'll get rid of the square root. So when all's said and done, the derivative of the inverse cotangent function is now, -1 in the numerator, and then this cosecant of the inverse cotangent squared is just 1 plus x squared in the denominator, or x squared plus 1. So I'll bubble that in. And again, notice how this is just the opposite of the derivative of the inverse tangent, right? Inverse tangent was 1 over 1 plus x squared for its derivative. Inverse, cotangent, -1 over 1 plus x squared, just the opposite expression. All right, so we're getting near the end here. We got 2 more. So again, we'll see these two are opposites. Right? We'll have inverse secant and inverse cosecant. So inverse secant. So the original function, the one I'm calling f, the one we're trying to find the derivative of, and this inverse secant, so SEC with the little -1 above it, of x, or, arc secant of x, same thing. And show you what that looked like again. So it's changing the cotangent to arc secant. So look, it had a highest point at -1 pi, a lowest point at 1, 0, and your domain was from -infinity up to -1, and then from 1 to infinity, right? You couldn't plug in values between -1 and 1. So the domain was -infinity up to -1, 1 to infinity, and the range, as you saw, 0 up to pi, but not pi over 2, right? If I put y equals pi over 2 here, that's going to be an asymptote in the middle. See the top half of the graph here is approaching pi over 2 on that side, and this is approaching a value of pi over 2 going that way. So 0 to pi. 0 to pi was the range, but not pi over 2. Still, 0 to pi, when I draw angles later, will be, quadrant 1 or quadrant 2, the top half of the xy plane. So once again, if this is my original f, look at the inverse. Right? So f inverse would be regular secant. Remember, to find the derivative of this function, I would have to start with the derivative of this one, right? So f inverse prime, remember the derivative of the regular secant was secant times tangent, so secant of x times tangent of x. And then I'm taking the function, original function here, the inverse secant, and putting it inside, for both of these, right? Anywhere there's an x in this, I'm replacing it with inverse secant. So applying the inverse derivative rule I've been applying for each of these, you have the derivative of f, so f prime, the derivative of this inverse secant function. The derivative of inverse secant is 1 over the derivative of regular secant, so secant of times tangent of, but not x, with the original inside. So secant of the inverse secant of x times the tangent of the inverse secant of x. And again, this is totally valid. This is an expression that would tell me slopes of tangent lines to this inverse secant graph. Tells me the derivative. But we want to write it algebraically. So once again, this inverse secant of x that's in these, that's an angle measure. All right, inverse secant of x is, again, I'll call it theta. This is an angle from 0 to pi, but not pi over 2, but something in the top half of the plane. So I'm going to draw both. So again, what if the angle is from 0 to pi over 2, right, as in the first quadrant? You got this picture here. And again, I want to set it up so that the secant of this angle is x. So remember, secant was hypotenuse over adjacent. And if those are the lengths of those, then the length of this other side by the Pythagorean theorem would be the square root of x squared, minus 1. Okay. All right. And we're asked to find, the secant of this and the tangent of this as well. Secant is x, now tangent of x, tangent of theta. So I got the secant of this, theta times the tangent of theta, down here. Or tangent's opposite over adjacent, so that'd be square root of x squared minus 1 over 1. Again, this would be a positive 1 length because, it's to the right. I'm on the positive side of the x-axis. So it's going to get tricky when we're on the other side because it got negative. Right? When I go to quadrant 2, this adjacent length will be negative, have a negative measure. They'll say it has a negative value, right? Because I'm on the left side of the x-axis. So over here, see how f prime would be 1 over, and then x times, again, secant of theta would be x, and then tangent of theta would be positive square root of x squared minus 1. That would be f prime, when my angle measure is in the first quadrant, right? Quadrant 1. But look at what happens, when I'm in quadrant 2. So again, I'll draw an angle here that starts there, ends in quadrant 2. Here's the triangle associated with that angle, and it has, this reference angle. I want to set this up so the secant of theta is some value called x. So again, that's hypotenuse x over adjacent, adjacent length, you know, would be, if you call that -1, you know, I could call over here x values are negative, right? When you're in quadrant 2, x is some negative number. Um, so remember how hypotenuse had to be a positive value all the time, so I can't just call this x. You got to call this the opposite of x to make it a positive value, right? If x is negative, opposite of x is positive. Because again, this length here would be labeled as -1. That way, when I do hypotenuse over adjacent, negative x over -1, I get positive x again, right? So in this picture with the negative x over -1, the secant of theta is still just, you know, x. You know, a little tricky, but it's because of this whole being on the negative side of the x-axis. And then this other length, which would be a positive measure, right? So it's because it's above, you know, it's on the positive side of the y-axis, would again be positive square root of x squared minus 1, right? Because you square that, it's x squared, square that, it's 1. You subtract them, take the square root. So over on this side of the x-axis, when the angle measure is in quadrant 2, the derivative would be, you know, 1 over, and then so again, secant theta is still x, but this time the tangent of theta, again, is taking the reference angle here is opposite over hypotenuse, opposite over adjacent. So it's the square root of x squared minus 1 divided by -1. So now you have the negative square root of x squared minus 1 for the tangent. So I'll make this negative down here. Okay. So see how it's a little different for different values of theta. You know, it's different when you're in quadrant 1, different when you're in quadrant 2. The major difference, though, can be kind of tied together by absolute value. See how I get x here when x is a positive value, right? Over in quadrant 1, x's are positive. I get the opposite of x here when x's are negative. That happens when you're talking about the absolute value of x. So you could express this instead of two different ways. You can bring it together and just call it the absolute value of x. You know, that way you get the opposite of x when x is negative, when you're in quadrant 2, and you just get x when x is positive and you're in quadrant 1. So a little tricky, a little trickier than the other ones. So overall, you'll see this in quite a few textbooks. The derivative of the inverse secant function is 1 over, and then this secant theta tangent theta, again, depending on where you are, could either be the opposite of x times the square root of 1 minus x squared, x squared minus 1, or just x times square root of x squared minus 1. But again, it's x if x is positive. It's the opposite of x is if x is negative. So you can just express that by the absolute value of x for short, times the square root of x squared minus 1. So this is typically how you're seeing the derivative of the inverse secant in a table. 1 over the absolute value of x times the square root of x squared minus 1. I'll say, for me personally, if you forget the absolute value symbol, you know, it's not the end of the world. It's technically not correct, but I wouldn't really take too much off, if anything, for that if I was testing you on this. Still, it's more technically correct, though, to have the absolute value of the expression inside your inverse secant function there. All right, so I'm going to go over a similar looking picture for inverse cosecant. The derivative of inverse cosecant, right, we'll see that it's just the opposite of this. Secant, inverse cosecant, it'll be -1 over this absolute value of x times square root of x squared minus 1, but we'll see that in a minute on the next page. So last one, inverse cosecant. So again, the function I care about, the one I'm calling f here, inverse cosecant, right? So CSC with the little minus 1 of x, or that arc CSC arc cosecant of x. Another refresher as to what that looks like. So it's changing SEC to CSC, right? So see how the lowest point is at -1, negative pi over 2. So the lowest it goes is negative pi over 2. The highest point at 1 pi over 2. So, and then notice it doesn't touch the x-axis. So the range, right, the angle measures I'll be looking at are from negative pi over 2 to positive pi over 2, but not 0. And then the domain is everything to the left of -1, including -1, and then everything to the right of 1, right, including 1, but nothing in between, right? You couldn't plug in values between -1 and 1. But still, the angle measures that are going to be mentioned here are from negative pi over 2 to pi over 2. So that's quadrant 1 angles or quadrant 4 angles, the right half of the plane when I go draw my pictures. So once again, looking at inverses, if f is inverse cosecant, then f inverse is the original, regular cosecant of x. The derivative of regular cosecant was the opposite of, or negative cosecant of x times cotangent of x. And like all the others, I'm taking my original function and putting it, inside this one. And then taking the reciprocal, right? So the derivative, so f prime, the derivative of this inverse cosecant function be 1 over, then the derivative of regular cosecant with the inverse cosecant put inside. So the opposite of cosecant of, the inverse cosecant of x times cotangent of, the inverse cosecant of x. And again, this is all well and good. We're going to ask, to write that algebraically. And like most of the other ones I've seen with a negative down here, I'm just going to put that up top, make this -1. So this will be -1 over, and then the cosecant of theta times the cotangent of theta, where, theta is this inverse cosecant of x. All right, and I said, we saw from the graph that this angle measure, right, this thing I'm calling theta, is from negative pi over 2 to pi over 2. So when I go to draw this stuff, it's going to be the right half of the plane. So again, here's where theta is in quadrant 1. So again, I set this up so that the cosecant of theta is x. And everything's positive in quadrant 1, horizontal, vertical. Again, hypotenuse always positive. Now cosecant would be hypotenuse over opposite. So this length hypotenuse is x, and again, x's are positive in quadrant 1, so that's still a positive quantity. And positive 1 for that length. And then this length still a positive, because I'm to the right here, I'm on the positive side of the x-axis. So it would be the positive square root of x squared minus 1. All right, so then in quadrant 1, the cotangent of theta is this, it's adjacent over opposite, square root of x squared minus 1. Right. Now if I'm in quadrant 4, right, so I draw my theta down here, draw a similar picture like this. So again, now this vertical length we'll call -1. So I gotta call the hypotenuse negative x, right? Because here in quadrant 4, x's are positive. Yeah, so let's still call this x. Yeah, x's are positive. Y's are negative though, right? So this and this vertical length is -1. And see now how the cotangent of theta would be, and look at the theta here, would be adjacent over opposite would be negative square root of x squared minus 1. So I would keep the hypotenuse x here, because again, positive length, and yeah, and then again, this I call this -1, and square root of x squared minus 1 over -1. So we get cotangent of theta is negative square root of x squared minus 1. So again, similar stuff happens where in one quadrant, we got a positive quantity in the denominator here, cosecant times cotangent. In the other quadrant, we have the opposite of that. So in a very similar manner to the secant, inverse secant, this isn't the greatest explanation, I do apologize. But similar to the inverse secant, we'll have -1 over the absolute value of x, just so I don't have to write both. All right, just to take both cases into account, times the square root of x squared minus 1. All right, so there's your derivative of the inverse cosecant function and how you're going to typically see it in most tables. But just like always, with the co-functions, they're opposites. All right, so really, you really only need to know inverse sine, inverse tangent, and inverse secant derivatives. Because if you know these three, the inverse cosine, inverse cotangent, and again inverse cosecant here, have just the opposite derivative. So again, despite the jumbled mess over here, right, that's key. All right, so we finally got all 6 inverse trig functions derivatives up. So now we can go back, finally, to the problems, right? There was only the one objective, and all these expressions should involve, inverse trig functions of some sort. So like for here, we're asked to find the derivative of g of x equals, 6 times the inverse cosine of x at the point where x equals, -2/5. And you're asked to enter an exact answer, right? Exact answer simply means as it is, without punching into some calculator or rounding to so many decimal places, right? Just kind of enter it as it looks. So here was our function, all right, g of x, 6 times the inverse cosine of x And then we're going to plug in, x equals -2/5 at the end to find the derivative. All right, so g prime. Remember, coefficients stick around, so it's 6 times, and then we saw this before. Right, again, it's that long opening part of the video on the derivatives of all 6 inverse trig functions. Remember, the derivative of inverse sine was 1 over the square root of 1 minus x squared. So this is the opposite of that, right? -1 over the square root of 1 minus x squared. And put the 6 up top there, right? So this is -6 divided by the square root of 1 minus x squared. And then we're plugging in, -2/5 and simplifying a little bit. So that'd be -6 divided by the square root of 1 minus, and then -2/5 squared. And I'll go through and simplify this a tad, right? So it's -6 in the numerator. Now, -2/5 squared would be 4/25, right? So we got 1 minus 4/25. This is -6 divided by the square root of. Now, this is 25/25 for 1. So that's, 21/25, which is -6 divided by, and then the square root of 21, divided by 5, and then multiply by the reciprocal of that. This would end up being -30 divided by the square root of 21. And this is how I'm going to enter it. That's a lot. That's pretty simple. Now, if you want to rationalize the denominator, you can multiply the top and bottom by the square root of 21. You can go a little further than this. So then you'd have -30 times the square root of 21 in the numerator, and then 21 in the denominator, and then 3 goes into 30 10 times, and 21 7 times. This would be -10 root 21, all over 7. This is probably how they're going to have it, because remember how back in pre-calc or algebra they wanted you to rationalize denominators a lot of the time, but they're only asking for an exact value. They didn't say anything about rationalizing denominators. So I'm going to enter that first one that I got with the -30, divided by, and then the square root of 21. Great. Yeah, see, they got the rationalized version of that I wrote. All right, so after you answer a question, they're going to tell you that you're right or that you're wrong and give you some sort of answer explanation. I'd highly recommend reading through the answer explanations, whether you got it right or wrong. If you got it correct, maybe they did something in a way that you like better and might want to try for future problems like that. Obviously, if you got it wrong, read through the answer explanations carefully. So hopefully you can figure out, where your mistake was and try to learn from that mistake for future questions that are similar. All right, so this time we have a chain rule going on here. See how it's inverse sine of not just x, but the square root of 5x, right? There's definitely a composition going here. So the chain rule is going to be involved. So we're given y equals, the inverse sine of something, right? Square root of 5 times x. Now be careful, the x is not inside the square root of 5 there. But yeah, so remember I said if you see the inverse sine of something and you go to take the derivative, it's 1 over the square root of 1 minus that expression inside squared. But then chain rule, you then have to multiply by the derivative of the expression inside, so I'll put like box prime here. So applying the chain rule, y prime, or I think they have it written here with that Leibniz notation, dy over dx. And it's the inverse sign of something, so 1 over the square root of 1 minus, and then that expression inside, so the square root of 5 times x squared. But then afterwards, times the derivative of the square root of 5 times x, which would just be the square root of 5. Remember, the derivative of a constant times x is just that constant. And then we simplify this. Numerators are just 1 and square root of 5. Multiply those, you got square root of 5 in the numerator divided by, and then down here the square root of 1 minus, and then 5 times x squared, right? Square root of 5 squared would be 5, and then x squared is x squared. So here's what I'll enter. Or you could put the whole thing in the square root, right? Make one big square root, because they're both in square roots here, and then have 5 in the numerator, and then, 1 minus 5x squared in the denominator. This should be the same thing. And that's all they're asking for, right? What would be the derivative function? So I'll just do that big square root, 5 in the numerator, and then divided by 1 minus 5x squared, squared in the denominator. As long as what you type in is equivalent to the correct answer, right? It should take it. Yeah, so you see they had it the way I originally wrote it. So there's another one where I'd have to use the chain rule, right? It's not just the inverse secant of x, it's the inverse secant of, and then some expression involving x. So y equals, inverse secant of, and then here we have the positive square root of 3x cubed. So again, when you see the inverse secant of something, right, when I go to do the derivative, that'll be 1 over the absolute value of that thing times the square root of that thing squared minus 1. But then don't forget, chain rule, multiply by the derivative afterwards, multiply by the derivative of the expression inside. So just kind of replace all the boxes here with, what's inside. So here, y prime, I've got the inverse secant of something. So it's going to be 1 over the absolute value of that thing. Now, because this is the positive square root, this expression is the positive square root, not the negative square root, you really don't need the absolute value here because it's already a positive quantity, implied to be a positive quantity. I mean, I'll put it because it can't hurt, right? It never hurts to throw, even if it's positive already, throwing absolute values around it doesn't make it any less positive, so it doesn't hurt to do that. Then times, the square root of, and then, our expression inside again, this square root of 3x cubed squared minus 1. And then after all that, multiply by the derivative of this. Now the square root of 3x cubed, this is the square root of 3 times x to the 3 halves power, right? Because you can think of this as, 3x cubed to the half, so it'd be 3 to the half, square root of 3 times x to the 3 halves. And then I can apply the power rule, right? So when I do the derivative of this, it would be 3 root 3 over 2 times, and then, x to the 1 half. Right, subtract 1 from 3 halves. So square root of x again. So 3 root 3 over 2 times the square root of x. And if you want to put the square root of 3 and square root of x together, this would be 3 times the square root of 3x, over 2. So 3 times the square root of 3x, over 2 afterwards, right? That's the derivative of the expression inside. And yeah, so I'm going to type it this way. Numerator, 3 times the square root of 3x. And then the denominator, you got, 2 times the absolute value of the square root of 3x cubed. And then times the square root of, and then when this is squared in here, gets rid of the square root, so you have 3x cubed minus 1. I'm going to type it in that way. Now, if you wanted to get rid of the absolute values because this is a positive square root already, that's fine. And then maybe combine this square root here with that square root, get rid of the square root of 3, and the square root of, and then the square root of x squared. Because x is implied to be non-negative anyway, would be x. I mean, you could simplify this pretty simply to get rid of the square root of 3 and get rid of one of the x's and make the square root of x squared into just x down here. So I think they're going to have it this way. 3 over 2x times the square root of 3x cubed minus 1. But again, I'm going to type it in this way with the absolute value and everything, just because it's not wrong. And it's the way that the derivative of the inverse secant normally initially looks is with that absolute value. So I have 3 times the square root of 3x, all in the numerator, divided by 2 times, say absolute value anywhere, absolute value of, and then the square root of 3x squared, 3x cubed, sorry, square root of 3x cubed inside there, times the outside the absolute value times the square root of 3x cubed minus 1, all inside there. That's what I had written. Just double checking. And that should be good. Yeah. Oh, that's exactly what they had. Wonderful. All right. So again, doesn't hurt to put the absolute value, that should technically be there initially when you're doing the derivatives of the inverse secant and the inverse cosine, right? You have this absolute value of an expression down there with that square root. Speaking of inverse cosecant. So again, remember the derivative of inverse cosecant will just be the opposite of the derivative of inverse secant. So here we had inverse secant in the previous problem. So here I have y equals, inverse cosecant of something, right? Now this is another one where I'll have to use the chain rule because it's not just x inside, it's a totally more complicated expression, 7x cubed plus 9. So once again, you see the inverse cosecant of something. When I go to take the derivative, it's going to be negative 1 over. It's going to be the opposite of what inverse secant was. Negative 1 over, and then the absolute value of that expression times the square root of that expression squared minus 1. Then after all that, times, the derivative, I'll put box prime here, the derivative of the expression inside. Okay, so applying that, using that, you got y prime equals, it's going to be negative 1 over, and then the absolute value of the expression inside, 7x cubed plus 9, inside the absolute value here, times, and then the square root of, and then the expression inside, 7x cubed plus 9 squared, and then minus 1 after. And then after all that, times the derivative of 7x cubed plus 9, which would just be, as a polynomial, would just be 21x squared. And I'm just going to throw that in the numerator, right? Negative 1 times 21x squared. So I'm just going to type out, negative 21x squared over all this, and that should be it for our derivative function. So negative 21x squared in the numerator, And then the denominator would have absolute value, which is in the keyboard here, of 7x cubed plus 9 inside that absolute value. Move out of the absolute value, then we have times the square root of the quantity 7x cubed plus 9 squared, and then minus 1, all inside the square root there. That should be good enough. Great. So again, that's exactly how they have it. Wonderful. All right, and that seems to be it, right? I think it looked like 4 questions there. So, the majority of this video is just going over the derivatives of the 6 inverse trig functions, which I'd highly recommend you know. Remember, as I said too, that if you know the derivative of inverse sine, inverse tangent, and inverse secant, then just take the opposites of those and you'll have the derivatives of inverse cosine, inverse cotangent, and inverse cosecant. So you really only need to remember 3 to know all 6. All right, so hopefully this helped you out in some way when you go to work on this on your own. And thank you very much for watching.